Good morning or good evening, depending on where you're at. My name is Atarot Azizin Amini, Director of the ABC UTC at Florida International University. Here, for those of you that who have not seen it, I'm delighted to tell you that the US DOT selected the FIU to lead for another term, which is going to be from 2023 through 2029. University Transportation Center devoted this time to innovative bridge technologies and accelerated bridge construction. So we will be covering all aspects of the bridge engineering, but also taking the ABC to the next level. You see our partner universities, so we're delighted to have them with us. We are going to be concentrating on bringing the latest bridge technologies, and we're going to reflect that in all our programs. So we have a request from you. If you have implemented any innovative technology in your projects, it doesn't matter what it is. It doesn't have to be ABC. It can be anything. Any innovative technology that you have implemented in your projects, please let us know. These are the kind of topics that moving forward in between the ABC projects, we're going to try to give a coverage. We are also interested if you you think that there is a certain technology that will help bridge engineering across the board. Again, doesn't have to be ABC. Please let us know. Drop me an email. It's very easy to find the email. My email, aazizina@fiu.edu. Okay. Let us have your suggestions because we would like to implement those in our activities. One of the activity that with the help of the industry or partner universities we are going to take on is development of the next generation of the asset management system. Most likely, it's going to be flexible to include both bridge and the pavement.
Our presentation today features the FHWA's lightweight concrete bridge design primer for ABC applications. We're pleased to welcome our presenter, Reid Castrodale, with Castrodale Engineering Consultants, PC, author of the primer as a consultant to WSP. Also, we'd like to introduce our Q&A session moderators, Jamal El-Kaizi, structural engineer with the Federal Highway Administration, and Jugesh Kapoor with HNTB and formerly State Bridge Engineer at WashDOT, both members of our ABC UTC Advisory Committee. We'll now begin the featured presentation. Reid?
Thank you very much, Mary Lou. I appreciate that introduction, and I'd also like to thank Atarot and Mary Lou and the whole FIU ABC UTC team for this opportunity to introduce a new resource on lightweight concrete, and that is FHWA's Lightweight Concrete Bridge Design Primer. And as I introduce it, I look forward to providing an overview of lightweight concrete for bridges. The primer, as Mary Lou mentioned, was developed for FHWA through a contract with WSP. So I'd like to acknowledge Andy Foden's contributions, who's now with HNTB. He was project manager for WSP and contributed greatly to the direction and review of the primer. I might mention the bridge in the photo here is the I-5 bridge over the Skagit River in eastern Washington, or actually western. It's a great example of a lightweight concrete bridge constructed using ABC methods, and I'll give some more details on that later. So there's a lot of information I want to cover today, and I can't provide all the details I would want to. So please do download the primer. It can be downloaded from the archive webpage at the FIU ABC website. And you can get many more details about what I'm talking about in that primer. I might just note as we get started here, this is the second time I've given a presentation on the FIU ABC monthly webinar series. I actually gave the fourth one back in July 2011, and it was also on lightweight concrete. And I guess I just thought I'd take a moment here on a personal note. I was just going to recognize Mary Lou Rawls' contribution to the success of this webinar, and she's been a very vocal and active champion of ABC for at least 20 years, and I've known her since I was at UT Austin in the 80s. And I just wanted to thank Mary Lou for all of your many contributions to the bridge engineering community. And then one final note before I jump into the presentation. I've hidden a few slides in the presentation in order to make available some more information to you that I couldn't cover in the presentation. So you may notice that some slide numbers get skipped. The hidden slides will, however, be available in the PDF of the presentation that's going to be posted on the archive website. There is a disclaimer here. I am giving a presentation essentially for FHWA here. So the primer was prepared for and reviewed by FHWA, and the presentation was also reviewed in its forms by FHWA. And this disclaimer is just indicating that the presentation provides information only and presents no binding requirements. So now I'll begin with a brief introduction to lightweight aggregate and lightweight concrete. You can see here that structural lightweight aggregate's been manufactured commercially in the United States since 1920. It started out earlier than, just a few years earlier than that. There was a patent that was gotten on it at all. So it's not a new material. Lots of us think of it as a new material. They immediately began using lightweight aggregate as it was available to make structural lightweight concrete, and it was used in bridges. An early application of it was the San Francisco-Oakland Bay Bridge. The upper deck of that suspension bridge was lightweight concrete, and I'll talk a little bit more about that in a few minutes. So what is lightweight aggregate? What we do is we actually, the suppliers of lightweight aggregate, they dig up the raw materials, a shale, a clay, or a slate, and they dig them out of the ground, and then they heat them in kilns. Those rotary kilns, very similar to cement kilns. You can see a couple of them where the arrows are on that photograph. In those kilns, the heat is fed in at the bottom, the raw materials at the top. The material gets soft as it gets down to the bottom. We don't melt it, but it's just softened. As you can see, it turns red hot. And then gas bubbles are evolved within that material. And then as that material comes out of the kiln, it's cooled, the gas bubbles remain, and the clinker then is crushed and screened. There are a few other sources of lightweight aggregate that are available, but my discussion is going to be limited to lightweight aggregates that are produced using this method, using rotary kilns. Where are the sources? Where is lightweight aggregate made in this manner? This map shows those locations. There are 13 plants in the US right now. 12 of the plants are members of ESCSI, the Expanded Shale, Clay, and Slate Institute, which is the trade association for all the plants that produce lightweight aggregate using rotary kiln technology. The website site is indicated here on the slide if you want to get more information. And you may think that you're out of luck if your location isn't close to one of those yellow dots on the screen. But just for your information, there's a project I'll talk some more. In fact, the project on the first slide, the I-5 over the Skagit River Bridge, actually used material coming from North Carolina, and it was shipped all the way up to Washington State, about 2,800 miles. We don't do that normally with normal weight aggregate, but in this case, it made sense. And it could still be competitive to use that lightweight aggregate because of the benefits that the lightweight concrete then brings to the table. So just about everybody listening to this is probably closer to a lightweight aggregate source than these folks were. A number of years ago, FHWA recognized that there was promise in using lightweight concrete for bridges. They felt like it could improve the economy and durability of bridges. So one of the strategies that they came up with to advance the use of lightweight concrete was to develop a lightweight concrete bridge design primer. And that primer, as shown on the screen here, became available last year, actually. It's available for download, as I already mentioned, from the Concrete Bridges webpage, but also from the webinar archive webpage. And the primer includes discussions of applications and projects using lightweight concrete, in some cases related to ABC as well as non-ABC projects. So I'll try to focus on the ABC aspects of it a bit today, more so than I have in some other presentations I've made. It does provide information on design methods and material properties that apply to any bridges designed and constructed using lightweight concrete. Here you can see the links there for obtaining that document. Here's the table of contents for the primer. I'm going to go into a fair amount of detail on chapter 1, or some detail on chapter 1, a fair amount of detail on chapter 2, as I introduce properties of lightweight aggregate and lightweight concrete. After that, I'll give highlights only for chapters 3 through 6. And then in chapter 7, project examples, I'll actually talk about several of those examples, but fairly quickly. I won't go through chapter 8, that's just the references, but there are over 160 references that provide information that supplements all the things that are presented in the primer, and also information about the projects that are discussed. As we get into what is lightweight concrete and lightweight aggregate, this is from chapter 1 of the primer. Lightweight concrete is defined in the LRFD. The definition is shown here, and it's simply a concrete mixture that contains lightweight aggregate. And it has an equilibrium density not exceeding 135 pounds a cubic foot. The term equilibrium density is maybe not familiar to some folks. The definition in ASTM is that it's the density of structural lightweight concrete after exposure to relative humidity of 50% and a temperature of 23 degrees C, room temperature, for a period of time sufficient to reach constant mass. And what it's talking about there is that lightweight concrete typically has some excess water in it because of the water that had been absorbed into the aggregate before batching, and that some of that moisture isn't tied up in hydration products, and as a result can move out of the concrete. So at any rate, the term equilibrium density is similar to one that you may have heard about previously if you've had any exposure to lightweight concrete, and that's air dry density. But that term isn't used any longer, and it's not defined in any specifications. So we are moving away entirely from using that term, air dry density, and just use equilibrium density. You may note that density and unit weight are sort of used interchangeably. That's not quite accurate, but that's the way it is in the specifications. So just to reiterate, lightweight concrete's not a new material. It's been in the AASHTO design specs since at least 1969. That's the oldest version that I had on my shelf here. And it's interesting to note that FHWA actually had a study back in 1985 that was performed by T.Y. Lin International. And they conclude in that study that lightweight concrete has, as you see here on the quote, a record of successful applications even back in 1985 to make it suitable for use in bridges. So that's just to help us to understand the context, that it's been around for a good while and it has a lot of performance data that's available. So what are the benefits for using lightweight concrete? Here's a list of structural benefits. Many of them have to do with the design efficiency for the superstructure and the supporting elements. It's especially true for seismic locations where reducing the load or the weight of the superstructure is going to significantly reduce foundation loads. Other benefits related to handling and transportation and erection where piece weights can be reduced. And that's something that we see, that would be ABC. Then the last bullet here is an important thing for ABC projects oftentimes, where if you're just replacing a superstructure, you could go back in and reuse the substructure. Things will move much more quickly. There was an FIU ABC webinar back in March of 2019 on an FHWA document about substructure reuse. Then 2 months later, in May 2019, there was a presentation on the Patapsco River Flats superstructure replacement project where they reused the substructure using an all lightweight concrete deck in that case. And then the Skagit River Bridge is another example, which I'll talk about more details in a minute. And there was a webinar in October of 2013 on that project. So here I'm highlighting some topics with ABC and then expanding one here. Prefabricated bridge elements and systems is what we often think about for ABC. And what lightweight concrete can do is to reduce the weight of the precast elements, both for handling, for hauling, for erection. We can use precast or pre-decked modular units where the deck is cast on the girders off-site, and then the whole span with deck is brought in and placed. We'll talk about a project like that later. And then even precast substructure units, which are oftentimes very heavy, can be made out of the lightweight concrete. One problem with precast substructure units is that oftentimes they may weigh as much as a long girder, but they're typically a whole lot shorter. So that can really pose some significant problems when you're transporting precast substructure units and meet load rating requirements on existing structures. And then the final bullet, again, is highlighted just since it is an important ABC strategy. What about other benefits? Interestingly enough, lightweight concrete has a durability benefit. It doesn't seem to make sense that using a porous aggregate in concrete would actually improve rather than degrade the durability of concrete, but that's what experience and testing has demonstrated. The pores in the aggregate that make it lighter actually allow the aggregate to absorb water prior to mixing, and then that is made available within the concrete after setting in order to cure the concrete from within, and this is known as internal curing. This feature really provides significant benefits of reduced shrinkage, reduced cracking, and reduced permeability. So it's a significant benefit to using lightweight concrete or just internal curing, which we'll talk about later too. There's what's called elastic compatibility. That is, the modulus of elasticity of the aggregate is lower, which is closer to that of the paste, and it reduces micro cracking. And then also we have reduced coefficient of thermal expansion, and when combined with a reduced modulus of elasticity, that really does a lot to reduce cracking, especially early age cracking due to restrained shrinkage, but also thermal effects, which are significant, especially in like decks that are restrained by girders. There are, however, perceived disadvantages of lightweight concrete in bridges, and you can see them listed here. Probably the main one is the cost of lightweight aggregate. Many people are very concerned about that, but the fact that many successful projects have been completed using lightweight concrete indicate that the increased cost alone can't deter the use of lightweight concrete. We shouldn't just look at that, and overall project costs have to be considered. Other concerns can also be addressed in design or with test data. And I'm going to briefly touch on 3 examples for bridges where lightweight concrete has been used, just to illustrate some of those benefits. And the first one is one we already mentioned, and that is the San Francisco-Oakland Bay Bridge. It was completed in back in 1936 using all lightweight concrete for the upper deck, the one that the cars ran on initially. So that was a 95 pound a cubic foot concrete. And it was, there's an article out there in, I think, ASCE that says that they saved $3 million by using that all lightweight concrete deck out of the original $40 million cost. Then later on, they reconfigured the lower deck to also be open for highway traffic, and they also used lightweight concrete there. And as I understand it, both of those decks are still in service. They have had wearing surfaces on them, but they're still there since 1936. And the benefit's pretty obvious with that reduction in cost, near 7.5% reduction. Now we're coming back to the I-5 over the Skagit River Bridge in Washington State. There was an overheight bridge that struck a span of the truss on that bridge, dropped it in the river. And when Washington State DOT put that back out for bid, they had a caveat that if the total weight of the replacement span was less than essentially the weight of the existing span, they did not have to, that is the design build team did not have to do a seismic analysis and retrofit on the piers. So that was a pretty good reason to try to keep the weight of the structure down. So the team that won, it was led by WSP on the engineering side, came up with the use of a sand lightweight concrete deck girder system. And that was the first time that lightweight concrete girders had been used by Washington State DOT. And the design compressive strength was 9 KSI. That was a specification, but the actual design compressive strength that is figured on the statistics and the compressive strengths in production of those girders came out to be 10.6 KSI. So it was a high strength mix. It worked well for this, and those were about 162 foot long girders. This same lightweight mix has been used on several other projects. We'll see another one in a few minutes. And then also these girders were assembled and then slid into place with a lateral slide over a weekend in order to open this bridge back up and remove the temporary bridge that was there. There was an FIU ABC monthly webinar on this project, and that was in October of 2013. And just as an example of the costs here, I think this is very telling. This is a table out of the primer, and it gives the relative cost, that is the cost of lightweight quantity to the cost of the normal weight quantity for each of these different items. And I'll click through each of them. The first one is aggregate. So the cost of the lightweight aggregate itself was 5 times that this plant would pay for their normal weight aggregate. The freight was 25 times the cost that they had for freight for the normal weight. And that's because it was being brought in some cases by truck, but typically by rail from North Carolina all the way to Tacoma, Washington. However, when you put all of that into the fresh concrete, into the concrete itself, the concrete, batch concrete was only 2 times more than the normal weight. Now that's still significant. But then by the time you get down to the girders themselves, the price per foot of girder was less than 15% more than for a normal weight girder. And I think that's very important to remember, that even though the cost of the lightweight and freight were so much higher for normal weight than normal weight, the cost of the completed girders was only 15% more. So that's a very important, and also what it is that the reason that the designers could look through this is they looked at the whole project and could see what the benefits from the whole project were going to be, especially since they could avoid the seismic reanalysis and retrofitting of those piers. That's important bear in mind. And have to remember too that this lightweight aggregate was shipped from North Carolina, but whether it was shipped from North Carolina or Texas or New York, Utah, California, it shows that even though the cost of the aggregate and freight can be a lot more, it can still make sense to use it. Another bridge is one that's not in the US. This is one up in Norway. It's a long span cast in place segmental concrete box girder over a deep fjord. As it was designed in normal weight, and then a peer review team said, oh, you ought to come up with a lightweight concrete design. So the lightweight concrete design had all these features that you see here. The main span was increased by 10%. And this is a project that, unfortunately, I don't have a photo of it here, but it's over a fjord. So by increasing the main span by 10%, you're moving the foundations up out of the deep water. So that was very significant. The bid for the lightweight design came in actually 15% less than for the normal weight design. And it turns out that once again, in this case, the contractor wanted to pump lightweight concrete, and the Norwegian DOT wouldn't allow pumping of lightweight aggregate, the local lightweight aggregate. So here, the lightweight aggregate was shipped in from the United States to this project, and the bid was still 15% less than the normal weight design. And that's because of the changes to the design that were possible because of the lightweight concrete. So now we're going to move on to chapter 2 and get into a brief discussion of the properties of lightweight aggregate and lightweight concrete. We'll look at some of the properties of lightweight aggregate, then some of the lightweight concrete, and then finally we'll just have 2 slides, I think, about internal curing. So there are a number of different sources of lightweight aggregate. There are 3 types, basic types: shale, clay, and slate, like in the name of the institute. Most of them are crushed. Some of them are uncrushed and are pellet shaped, like we're in that picture. There are gradations that exist, both AASHTO and ASTM specs that specify the gradations for these aggregates, both coarse aggregates as shown here, and also there are fine aggregates that are available. Absorption is an important property for the lightweight aggregate because lightweight aggregate is expanded and it has pores in it. Those pores or holes reduce the density of the material. The absorption typically ranges somewhere from 5% to 25% by mass after you soak it for 24 hours. And it does depend on different lightweight sources and size. But it is important that absorption alone should not be considered as the single determinant for acceptable performance. That is, a low aggregate is not necessarily going to give you, an aggregate with a low absorption is not necessarily going to give you better performance in some applications than an aggregate with a higher absorption. And in some cases, that's been written into specifications. But that's just something to be aware of. Here's some data just for an example. This is absorption data. You're seeing a number of different sources. Pretty much all the sources in the US for lightweight aggregate are on this plot. And you can see that at 48 hours over on the right side, the absorptions are ranging from about a little over 6% all the way up to a little over 32%. But it's an interesting fact that if you normalize all this data to the 24-hour value, the behavior of all these different aggregates is really very similar. They gain absorption very quickly, and then it flattens out and continues at a much slower rate. One thing that people often think is that lightweight aggregate must be like a sponge and the water can just come in and flow right through the aggregate and all the pores are connected. And that is not the case. And this is a little bit of recreational mathematics that I did based on the original specified density, the expanded specified density, and the absorption. And you can put those things together and actually come up with similar figures to this. This is for one type of aggregate, one source of aggregate. The gray area is the solid portion of it. The white area, including the blue area, is the void, and then the blue area is the absorption. So you can see here that while about half of this aggregate particle, a 3/4 inch particle, is made up of voids, those voids are not interconnected. So the water can only get into a small fraction. In this case, it's less than 10% of the aggregate. And so it's filling only about 20% of the pores. So that's important to bear in mind. You see it does vary as far as between the different gradations. You actually fill more of the pores on the fine aggregates than you do on the coarse aggregates. So much of the void space remains unfilled. We never saturate those aggregates and fill up all those pores. What about the durability of lightweight? Lots of us think, can a rock with voids or pores be made a durable concrete? This is some data from North Carolina DOT, picked it up in, I think, 2013 or no, 2020. It has the average for the soundness test and the LA abrasion for all aggregate sources on the list. You can see here 73% for soundness, 31% for abrasion. And then there are 2 lightweight aggregates that are manufactured in North Carolina, and they're on this list. Both of them have values for these tests that are equal to or less, essentially equal to or less than the average for all of the ones in North Carolina. And they're well within the requirements that are down here on the bottom, which are the NC limits for those test methods. So while many people think that lightweight concrete isn't able to meet the normal weight aggregate, that is, lightweight aggregate's not able to meet normal weight specs, indeed it can in some cases. And that's what I'd recommend, that except where it's not possible, you would stick to the same requirements. When we get to lightweight concrete, there are some different definitions. We have all lightweight concrete, which is where all of the aggregate in the concrete is lightweight. Sand lightweight concrete is a mixture that has coarse lightweight aggregate and normal weight fines. And then specified density is any kind of a blend of normal and lightweight aggregates to obtain some specified density. These definitions aren't in the LRFD specs anymore. They used to be, at least the first 2 were. Now we simply are specifying the density of the concrete, and the supplier defines how you mix that up, how you combine aggregates. What kinds of densities do we have? A fresh or a plastic density is important because we use that for acceptance at delivery. And then an equilibrium density is what dries out, and this would essentially be your service or your long-term density that you would use for dead loads at the service condition. Might just note again that density and unit weight are oftentimes used interchangeably in the specs. Typical range of densities, it's given in the primer. For lightweight concrete, typically from 110 to 125. You can get lower. You can get all the way down to maybe 90 pounds a cubic foot, maybe 100 pounds per cubic foot. The specified densities are, as they are for normal weight, or for plain concrete, so you do have to add an allowance for aggregate when you're computing dead loads. Hardened mechanical properties for lightweight concrete are important. A lot of people feel like lightweight concrete has reduced mechanical properties compared to normal weight. And that's really only true specifically for the modulus of elasticity. That's the most significant one, but many of the others are essentially similar. And in some cases, they can even have better, lightweight concrete has better properties than normal weight. So there's a lot of information that is in the primer that you can learn more about that. For compressive strengths, you should check with available lightweight aggregate sources to find out what's a reasonable upper strength. And in some cases, you can make some compensation as it's indicated here. Also, that's for decks. You know, we can easily achieve typical deck concrete strengths. For girders, probably can get up into the 8.5 KSI, and some aggregates can get up to the 10 KSI range. And that's something that has been shown in a number of different projects. Tensile strength, oftentimes people think that tensile strength of lightweight is going to be reduced compared to normal weight. There was a study done in Auburn University. This is data from that study. And in this case, the splitting tensile strength is shown here, the compressive strength here, and the ratio of splitting to the expected splitting tensile strength for normal weight concrete is shown in this column. And we actually find that all the lightweight concretes have something greater than 1, where the normal weight, which was a river gravel, it had the reduced tensile strength. But we don't make any modifications for that. But typically we do modify these sand lightweight mixes in some aspects. So that's just interesting to note. As far as the modulus of elasticity, there's a new equation. There is a reduction of modulus with the reduced density, and that's included here with the unit weight being in the calculation for modulus, and that's been in specs. This is a new equation, but the old equation also had the unit weight, and that's been done since the 60s. We've been recognizing that reduction in modulus. There is an awful lot of scatter in those data. Here's some information from the concretes used for girders up in the Northwest. We have creep over here and shrinkage over here, and the red lines are for lightweight concrete. The green line is for normal weight concrete. The creep coefficient is actually less for the lightweight concrete than the normal weight, and the shrinkage is less for the lightweight than the normal weight. And what's really interesting on this one, especially for the shrinkage, is that the lightweight concrete mixture has like 24% more cementitious material in it than the normal weight mix. And conventional wisdom is if you have a much greater cementitious content, you're going to have more shrinkage. And this is showing the opposite, actually by a fair margin. So that's the benefit of internal curing. Coefficient of thermal expansion is also reduced significantly. More data from the Auburn study shown here, and that can be very important for cracking tendency, especially of decks where they heat up when they're hydrating after pouring, but then they lock into the girders, and then when they cool off, they get a significant thermal stress and can have early age cracking, where this, along with the lower modulus, can compound to have a significant reduction in cracking tendency for a lightweight deck. Here are some, I'll say that there's more discussion following then in chapter 2 about, well, what properties do we use for design? And each of those different types of properties that we use are discussed. There are provisions in the 8th edition. They've been revised in some cases now, but we do have all of that available. There are properties for lightweight concrete. Those are durability, and those are all discussed as well. Background for that is given. And I can't discuss it further, short on time today. Internal curing is discussed slightly, and what we typically do when we talk about doing an internal curing mix, which is something that FHWA now has in their Everyday Counts 7 program. They've labeled it as EPIC 2, but that's internal curing, where you take some fraction of the sand out of a conventional mixture and you replace that with pre-wetted lightweight aggregate, and then that pre-wetted lightweight aggregate then provides the internal curing and does have a significant improvement to the properties, even though it's only a fraction of the sand that's being replaced. And here's a very graphic illustration of that. This was a trial placement for a big water tank, but the mixture on the left side, well, this photograph is showing you what the condition of those trial placements were the next morning after you had a internally cured mix placed exactly right next to a conventional mix. No curing compound was placed on either of the concretes. And the next morning they came out and the internally cured concrete was still moist on the surface, where the surface of the non-internally cured mixture had dried out. So that's a very graphic illustration of the benefits of internal curing. We're now going to hit the next three chapters quickly. Chapter 3 gives initial design considerations. So what do you need to use for design? And this steps through the different points that we need for different applications and stuff. So I think this is a very important chapter to have. Chapter 4 goes into design aspects of using lightweight concrete. There were some changes that were adopted in 2014 and 15. Those are discussed, and then we go through some other sections. I'm getting short on time. I'm going to have to turn on the afterburners. Here are a couple of highlights of some of those revisions to the specifications that were made in 2014 and 15. The designer now specifies the unit weight. We always did that, but then that is used to define the density modification factor. So it depends on the actual unit weight specified rather than just an all lightweight or a sand lightweight designation. Another thing is that the resistance factor for shear used to be 0.07, where it was 0.9 for normal weight concrete, and now the shear resistance factor for lightweight is equal to that for normal weight at 0.9. There was a new modulus of elasticity equation, and then creep and shrinkage, pre-stress losses. It's been found by research that we can use the exact same values, equations that is, that are computed using the standard equations without modification when we're designing for lightweight concrete. As far as construction, there's some discussion of different things that people need to look at in order to get a successful project. Chapter 6 is about how to specify lightweight concrete. That's also very important in order to get a successful project. And then we move into the project examples. There are 3 types of categories of projects that we had, and you can see them listed here. And also we had quite a range that we included there, for a range of bridge projects, large and small. Some of them were decks, girders, segmental bridges, suspension bridges. And there was no mention here about internal curing in the projects, but there are references. A couple of projects I'm going to discuss. The beach bridge here in Maine. It was next D beams that were used to replace a small 2-span bridge on an island off the coast of Maine. It was the first use of sand lightweight for next beams, and it was a successful project. They needed to use lightweight concrete to be able to reuse the pier. It avoided the design and construction of new foundations, which were pretty difficult at this site, and also, since it was an island off the coast, shipping and handling was significant, so reducing that beam weight was important. Here are some more projects that reused existing structural elements. I'll just touch on one, and that is the Ben Sawyer Bridge in South Carolina, where the deck on the swing span was placed with lightweight concrete. It was brought in from off-site. The new deck on the approaches was cast offline and then slid into the new, into the old alignment, moving off the old bridge. So the foundations were able to be reused with that lightweight concrete deck. A couple of other projects that we have here where improved structural efficiency was important. The Benicia Martinez Bridge outside of San Francisco is a major bridge with spans up to 201 meters or 658 feet. And the entire segmental box girder section there was lightweight concrete. This was completed in 2008. So the whole bridge, except 6,500 feet of bridge, except for the pier segments, were lightweight concrete. And that use of lightweight concrete greatly reduced the seismic forces and therefore the foundation size and cost. There was a similar span, 640 feet, that was constructed way back in '79 in California. And it had to be retrofitted because of excessive mid-span sag. And I can't go into the details of all that, but there was no problem with the Benicia Martinez Bridge with sag. So the creep and shrinkage were handled appropriately, and it wasn't excessive, and it was a successful project. Projects that have reduced weight for shipping and handling, there are 3 of them here that I'll touch on briefly. One is the longest single piece girder that's been fabricated in the US. It's 223 feet long, but it has huge skews on the end, so it adds 7 feet. Big girder used the same lightweight concrete mix as was used in the Skagit River, and they used the lightweight concrete in order to be able to build this thing and ship it, because they couldn't have shipped it otherwise, even though they're going about 7 miles or something to the site. This is a project in Richmond, Virginia. It's 2 projects. One was early 2000s, and then one was later in the 2014 or so, where the deck is placed on steel girders and the whole unit is then replaced overnight, replacing a span at a time or half a span transversely. And the lightweight concrete was very significant in reducing the weight of those elements. Also, it made it more resilient for difficult mix and environmental conditions. And this deck is not covered. The lightweight concrete deck is exposed and it's performing well. Last project is a big one, the biggest spliced girder span in the US right now, 325-foot main span, and lightweight concrete was used for the drop-in span. You can see those girders, they were actually put in pairs and lifted in pairs using strand jacks. And the lightweight concrete assisted in making that possible. So that brings me to the end. This is the final slide. I have Reggie Holt's contact information with FHWA shown here. He's the concrete fellow there that supervised this work that we did in writing the primer. And I encourage you to download it, and I think we're ready for questions and answers. Thank you very much.
All right, Reid, thanks for the excellent presentation. Lots of good information. So at this point, we're gonna turn it to Jamal and Jugish, I believe, to go over the question and answer period. Jamal?
Thank you, Atarad and Reid. That was a great presentation. We have a lot of the questions that came in during the presentation, and we have more came in before the presentation. So let's get started here. First question, Reid, is about anchorage. And how does the anchorage design differ between lightweight concrete and normal weight concrete?
Okay, thank you, Jamal. I appreciate that. That's a good question. And really the only way that lightweight concrete can affect anchorage in concrete, either development lengths or post-tension anchorages, either one, is the potentially reduced tensile capacity of lightweight concrete. And this is accounted for in the design using a lambda factor. However, in the LRFD, there's actually an option to allow us to specify the splitting tensile strength. And if you specify the splitting tensile strength equal to the expected splitting tensile strength for normal weight concrete, that lambda factor can go to 1, in which case there's no difference in the design between a normal weight design and a lightweight concrete design. And some of the test data that I showed you indicated that the lightweight concrete did indeed have a splitting tensile strength that was equal to or greater than the normal weight. So I think it can either be handled by design or even improved by specifying the splitting tensile strength for the anchorage. I hope that answers the question.
That's a great answer, Reid. We have another question, talk about properties of the lightweight concrete, which is creep behavior, deflection, and shear. There's questions that came in during the presentation, talk about excessive deflection as well during using the formula for the normal weight concrete. However, you mentioned there's a new formula, and you did that in your presentation, using lightweight concrete for modulus. Could you elaborate on creep behavior, deflection, and shear?
Okay. As far as creep, I mentioned the Parrots Ferry Bridge. There are a lot of old timers, because that was built in '79, that feel like that bridge demonstrated that there are creep problems with lightweight concrete because it ended up with a sag. I mean, you can see it if you go over it right now. It has a sag. It's been retrofitted, but there are a number of factors that contributed to that. Not the least of which is there's no positive moment tendons in that. There's no continuity tendons crossing that midspan. They only had cantilever tendons. So the design was somewhat flawed, as well as some other issues as well. So we did see the Benicia Martinez Bridge is doing fine. There's no sag on that one. The deflections are not unexpected. So we do have long span bridges. And I didn't mention it, but in Norway, there are 3 cantilever constructed segmental box girder bridges that are 300-meter spans, almost 1,000 feet long. And they use lightweight concrete in their main spans. So they've been able to deal with it if you construct it appropriately and know what you're looking at and use the right values. You can build those bridges so that deflection is not a problem. You will have more live load deflection because you have a lower modulus that's coming from that equation. But typically we're still within range. We don't exceed anything there. As far as shear strength, we've seen a lot of bridges that have been built. So you can typically deal with it by adding a few stirrups if you're using a lambda that's reducing your shear capacity. But we also have the opportunity to specify a lambda, which could get rid of that difference if we wanted to. So hopefully that gives you some information. Again, the primer has a lot of information in more detail on all of these questions. So I'd encourage folks to look there.
Yes, and like Reid mentioned, you can download the primer free of charge. There's a link right there in the handout box. You can download it from there, or you can go to Google and just Google FHWA, the lightweight concrete bridge design primer, and it will take you to the Office of Bridges and Structures, and you can download it from there as well. Another question, Reid, here they're talking about the wind load design on the bridge substructure, and the question is, how does the use of lightweight concrete affect the wind load design on bridge substructure?
Well, that's an interesting question. There was a project, now I can't remember, the Milton-Madison Bridge, I think it was, where I had suggested to some folks, this was a large river bridge truss, and I suggested, well, maybe you ought to put lightweight concrete on that deck. Well, turns out they needed the weight of the deck in order to give you the stability you needed for the foundations because of the wind loads on the big truss. So there are a very few cases where you may not want to have lightweight concrete. In other words, you may not want to reduce the weight of your superstructure if wind is a significant factor on your substructure design. But in most cases, I think that will not be the factor. But you just have to bear that in mind if you're looking at the design.
That's correct. Usually that would not be a major concern, because for wind load design, you're looking at the exposure, the fascia exposure, and on the superstructure as well as on the substructure. And the difference in weight is not that significant to affect the design. So I think you touched on it accurately, Reid, here. Another question on pre-stressed concrete. Is lightweight concrete applicable for pre-stressed use? And what is the specification for lightweight pre-stressed concrete?
Okay. As I showed some examples there, hopefully folks saw it, that we've been making pre-stressed girders. In fact, the longest one in the US is lightweight concrete. So it can be certainly done. The one on the picture on the right there that's on the screen right now is a lightweight concrete girder, is 160 some feet long. So there are provisions in the specifications. There's guidance in the primer for writing construction specifications. And there's really no structural reason not to use lightweight concrete for pre-stressed or even post-tensioned members. They've been constructed both ways. So I don't know if that's a good answer. I mean, I could go on and on, but I think for this purpose, hopefully that'll be adequate.
It is, and the primer has more information about the design, as well as there's an AASHTO specification on lightweight concrete. Now, the next question, Reid, is there's two parts to it. One of it came during the presentation, and one of it before the presentation. You touched on the advantages of lightweight concrete versus normal weight concrete. And the question is why we are not using it more. And there's a related question where they said they had some problems in the past for bridge decks where the concrete was deteriorated due to lightweight concrete, and how that is changed now with the new specifications.
Okay. Well, that's a good question. There are a lot of different factors involved, including some of the industry stuff. There's a slide that's hidden, slide 6. Maybe I could even show that. Well, maybe I won't. Slide 6 mentions the fact that at one point, ESCSI had tremendous promotional activities, and then through a number of different issues, the production reduced. Not any structural problems or anything like that. It had to do with regulation and EPA and things like that. So they stopped promoting. So that's one of the reasons why we haven't had lightweight concrete being promoted like it could be and used as it could be. Many designers think that there are a lot of different properties that are different. I've shown you there that we can design for them. The specs address those properties. The main issue for many people is cost, but again, they oftentimes stop just looking at the price of the aggregates. Many times, like in that figure that I showed, the table I showed, the price of the aggregate was 5 times that for the normal weight aggregate. Well, it turns out that you can divide that in half immediately because you get twice the volume per ton as you do for a normal weight. So because of the difference in density. But at any rate, you need to look at the overall cost. And we've seen these projects that are very successful that have used lightweight concrete. So it's pretty obvious that they weren't throwing money away, but they were being good engineers, and they looked at the whole project and they understood that they could save the money by using lightweight concrete. Even though concrete costs more because of other benefits, such as foundation reduction, reducing seismic effects, that's important. One thing, we do have some issues from the past. I know Alabama has had some. Up in Washington State, they had, or in Alaska, they had some issues with lightweight concrete years ago that deteriorated quickly, relatively quickly in the decks. And that can come from a number of different factors. Oftentimes it has to do with not constructing things appropriately, or using some material that maybe wasn't in spec at the time. It's hard to know, but it's been years. And we're seeing things like the San Francisco-Oakland Bay Bridge, where the same deck is in service since 1936. Number of years ago, for ABC projects, there was one of the early poster children for that was the Lewis and Clark Bridge over the Columbia River. It was built in 1930, and it had an all lightweight concrete deck. It lasted until the early 2000s. So we know that there is evidence that the decks can perform well. There have been a few poor performances, as there are with normal weight. So we just need to bear that in mind. Hopefully that's adequate. Is that good, Jamal?
That's a good answer, Reid. Another question about concrete bridge barriers, and can the application of lightweight concrete is used for MASH compliant bridge barriers, and are the state DOT using lightweight concrete and bridge barriers?
Yes, that's an interesting question. It's one that I've tried to track for a number of years, and I'm not sure that I have the final answer on it. But MASH is also a different animal a little bit than the previous types of barriers. There are a number of states that have been using lightweight concrete for barriers. I am not aware, however, of any testing of lightweight concrete barriers, physical testing, crash testing of barriers, but it has been used successfully. And some of the people that I have talked to from the barrier testing world feel like that they would expect the performance to be essentially the same as normal weight concrete if you have the same compressive strength and the same tensile strength, roughly. So they feel like it should perform just as well. So I can't give a definitive answer on that, other than I do know that there are states where they are using lightweight concrete barriers.
Great answer. You mentioned about the durability and service life of lightweight concrete compared to normal weight concrete. So is there anything else you want to add to this one? There is a question on that one.
There's so much that's involved. Again, it's unexpected. You know, to show me a rock with holes in it and tell me that this is, you know, if you put this in your concrete, you're going to have more durable concrete, or at least equal durability. That's a little hard to believe. But as it turns out, because the pores aren't connected, the aggregate doesn't fill up with water. We have an example of freeze thaw testing, where you've taken, there were 4 specimens that were cast. 2 of them were tested as they came out. These are of lightweight deck concrete. And the other 2 specimens had the faces sawed off the specimens to expose the interior of the lightweight aggregates. Those were tested using the standard test procedures. They were all tested the same, and there was like 2% difference between the normal tested versions and those that were exposed aggregate on all faces. So just the fact that you have exposed lightweight aggregate because of grinding and grooving on a bridge deck, that does not mean you're going to have poor performance. It should perform very well, as was demonstrated in those test results. There are photos of that in the primer.
Yes, yes, and these questions, they came in before the presentation. That's why you already covered a lot of it in the presentation. They're asking about the track record of bridges using lightweight concrete, and you showed some examples in the presentation about the bridges used using lightweight concrete. Is there any more information you wanna add to the track record of using lightweight concrete on bridges?
I know that there are some bridges, there's some pre-stressed girders that have been in service. Both, there are two bridges at least in Florida, and there's the San Diego Coronado Bridge has lightweight girders in it. Those have performed very well over the years. So I know that we have examples of long-term performance of lightweight concrete, both as girders and decks, already mentioned on some of the decks.
All right, all right. One more question came before the presentation, and they're talking about the testing, AASHTO and ASTM testing of lightweight concrete as related to the fiber reinforced polymer reinforcing, and they're looking for the bond development, etc.
I am not closely familiar with that, but I would expect that it should be essentially the same. If the reinforcement bonds to normal weight in a regular way, if there's not anything special that has to be looked at there, then I would expect that the same would be the case with lightweight concrete. I am not aware of testing. However, there has been some, I believe that there may have been some testing on that, but I'm not positive.
And I agree with you. There should not be anything different between lightweight concrete and normal weight concrete as far as bond. Now there's this question came before the presentation, but you covered it about the aggregates. What type of lightweight aggregates? And you mentioned the type of aggregates used in the lightweight concretes. So the question is, what kind of aggregates are used for lightweight concrete?
Yeah, so the aggregates that I discussed earlier have been manufactured. There are some other aggregates that may be available in certain spots in the U.S., but they are not, the ones I am talking about are rotary kill expanded shale clays or slates. And that's basically what the U.S. specifications are addressed to. For example, in Europe, their aggregates do not perform quite as well as ours do. They have mostly expanded clays that are pelletized, and they seem to have reduced properties in some ways compared to ours. But ours are fairly uniform in the ways that they behave from the different sources. Some have capability of getting a little bit higher strength than others, but not all. So I'm not sure if that answers the question very well, but I think that's probably good for now, hopefully.
Oh, okay. All right. There's questions came during the presentation and one before, and they're talking about price. And you covered that in your presentation, looking at total project cost. When it comes to lightweight concrete, that would give you more a good estimate than just an item. Here they say, when will the price come down for lightweight concrete? And another questions, they're talking about how that compares to the cost of ultra high performance concrete.
Wow, that's a little tough to figure the second one, the UHPC. And there's actually some people who've been looking at using lightweight aggregate in UHPC in order to provide internal curing to hydrate more of that cement, because in UHPC it has such high cement content and low water cement ratios that you don't hydrate all the cement. Some of the cement is just being used as filler. So if you use the pre-wetted fines, you wouldn't want don't want coarse aggregate in there, of course, but if you use the pre-wetted fines, then you may be able to take advantage of some more of that cement and hydrate it rather than just using it for filler. Gee, now what was the first part of the sentence, the question?
When the price come down.
Right, okay, yeah. And the price, as you remember in that early slide, lightweight aggregate is expanded in a kiln that is fired in order to get it up to about 2000 degrees Fahrenheit. So there's a significant energy input. There's also a significant transportation factor that is oftentimes included in that. So we'd love it if there was something that the industry could have to be able to reduce those production costs and transportation costs, but we still see that it can make sense even at the higher costs, as was shown in that table, where it's being shipped 2,800 miles across the country, in some cases by truck, and it still makes sense for a project to use lightweight concrete. We hope that somehow we can get the price down, but with that much energy input to heat it up, I'm not sure we'll be able to do that, or that they will.
Great, Reid. You covered all the questions that I have. I'm gonna turn it now to Yogesh to cover some more questions that came in during the presentation. Yogesh?
Thank you, Jamal. I have 15 seconds to cover the questions, so I'll just shoot one out. Can lightweight concrete be used in link slabs?
That's an interesting question. It's probably a beneficial one because it has lower modulus of elasticity. Therefore, as link slabs are subjected to deformations rather than strength issues lots of times, with the lower modulus, it should reduce cracking in link slabs. So I see that it could be beneficial for that application.
Okay, thank you.
Yogesh, we do have time for 2 more questions if you want to. Go ahead.
Okay, I'll address 2 more. How much variability can be expected in specific gravity, density, unit weight of lightweight concrete? Lightweight aggregate, yeah.
Yeah, how much variation in the aggregate, I guess, is the question there. I mean, we have specifications that have to be met for both that, well, mainly for the concrete that's produced from it. There can be variation, just as there is in normal weight aggregates. There will be variation in different properties since it's a natural material, in this case, that's been processed. Since it's a manufactured material, the plants do have some ability to blend their materials on the backside of the expansion so that they can get a more uniform product. So it would have a more uniform specific gravity or density or whatever you're looking for. So I can't speak to particular numbers, but there has been lots of successful projects that have been able to be done keeping within the parameters that are specified.
Okay, thank you, Reid. One more question, and this would be the final one. Why does it appear that lightweight concrete has not caught on more due to the benefits that we are seeing of it?
Yeah, and that sort of goes back to some of that earlier discussion that I had about a cutback in promotion back in the 70s when a number of things converged to actually have a contraction in the industry, and they stopped promoting. They let all their engineers go. And, so that's part of it. And then the other is that people just haven't been looking at the full project perspective. We've had projects that have been occurring over the years that have been successful, like the Benicia Martinez, and there are all sorts of others. I'm managing technical editor emeritus of Aspire magazine, and we have quite a number of lightweight concrete bridges that are reported in that magazine. So we're still building them. The Skagit River Bridge, where lightweight concrete is. So people who understand its benefits use it, but most of us are reluctant or uninformed perhaps, and aren't aware of the benefits that are available. So I think that there should be opportunity for using lightweight concrete on a lot more projects than it's being used.
Okay. Thank you, Reid. I'm out of time, but the answers to the remaining questions will be posted online. So appreciate your answers and doing this webinar. Thank you very
Great.
much. Back to
Thank you,
Atara.
Yogesh.
Thank you, Yogesh. Reid, if I just have you just for a couple of more minutes with me. So thanks for the great presentation. This was very informative. Again, before we sign off, just to our audience, as we mentioned, we are in the process of starting a very major project, which is related to next generation of the asset management system. If you have significant experiences in bridge asset management or pavement asset management, and interested to be a member of advisory panels and be involved with this project, please, by all means, send me an email, aazizina@fiu.edu. Also, as I mentioned, that if you have any suggestions related to any topics, innovative technologies that can help bridge practice in the US, it doesn't have to be ABC, any aspect of the bridge engineering, please let us know. If you have any project that has incorporated any innovative bridge technologies, please let us know, because we would love moving forward because of the change in the nature of the ABC UTC. We're going to be devoting monthly webinars to these topics, the innovative technologies. So please share with us any projects that you have had that have incorporated any innovative bridge technologies, so we can consider them in future for monthly webinars. So on that note, I would like to say thank you to join us, and until our next monthly webinar in July, so long. Thank you.